I've got the notes up here, or I mean the weekly schedule here, and I wanted to just point out quiz 8. If you haven't looked at my solutions to that yet, you should take a look at that, and I'd like to talk about it, and I'll pull it up here in just a second. But that's a quiz we took last week on Friday, and it was definitely the hardest quiz we did and sort of the lowest average, I think I would describe that. So I'd like to make sure that's clear. That was about optimization and implicit differentiation. So take a look at I passed it back over the weekend. Take a look at the solutions to that. They're also on Blackboard if you want to take a look at that, and we can look at that in a second. There's a couple of web works due as always this week and next week, and I kind of want to be clear about it this week. I am not going to extend, so will not extend these. I'd like to get back on track here, and I've already looked, almost no one has started that. One person has started that. Thank you for that person. It's fine, but I'm not going to put them back. So just know that you've got to finish them Wednesday. I suggest you look at those before Wednesday, so that if you have some questions about them, we can go over them. And if you want to wait until Wednesday to start them, that's fine, but I'm not going to extend them this week. Partially, I want to get back on track because I want the next ones to be due next Wednesday without a problem, and the material for this Wednesday we've already covered. So there's really no reason we can't. And then we've got our next test coming up in a couple weeks. So by the end of this week, I will have all the review stuff posted for that. All right. Yeah, I think that's all I wanted to say there. I'm going to pull up the quiz solutions real quick, and I would love to hear from you about them. Oops, they're not in there yet. Give me 1 second. Let me put them into my drive real quick. It's one of the best parts of using Google Drive and my iPad. I could just drop it right over on my computer. If I open it up right, let me open it up. It'll pop up on my iPad. Okay. All right, so this is the quiz that we did on Friday. The first one was the optimization problem, and I just wanted folks to set it up. I just see in the chat, someone asked, let me just back up real quick. Someone in the chat said, what will the quiz be on? So it does say right here, the quiz is going to be on related rates and L'Hopital's rule. The question was, will our quiz Friday be on L'Hopital's rule? So that's what it'll be on. It says right there, right? It's the homework that's due Wednesday, right? So this homework is the one that I'm not going to extend. It's the one that we're going to finish on Wednesday, and then we'll have a quiz on the homework on Friday. So it'd be great if you wrote down your solutions, bring them into class, crush the quiz. Other questions before we look at the last quiz? Okay. So on this optimization problem, I just wanted you to set it up. And in both of my sections, I sort of went over how you should set it up. I think I even sort of said what the objective function should be. We talked about the constraint, and there was still a lot of confusion on how to do this one. So please let me know if I'm going to ask you to actually solve one of these problems on the next test. And so setting it up is the first step, right? So here, let me just sort of highlight the key things. We want to make a box. We only have 10 square meters of material. Okay, so that's the constraint. So that's going to apply down here. We want to build the one with the biggest volume, right? The maximum volume. And so that's the objective function. And I think most people sort of were at least on track. And a lot of people in the part B were like, oh, we only have 10 square meters of material. And that's true, but we want to actually write down the mathematical constraint associated with that. And in both classes, let's go through them one by one. So in the maximize the volume. What's the volume of a three-dimensional object? You just do length times width times height, right? And in this case, two of the dimensions are the same, so that's why you get double x, right? And that's what leads to the x squared. So x squared y would be the thing we want the max of. Questions about that part, the objective function? So I think some people did like x squared y equals 10, for example, right? That would be the volume being 10. That's not what the constraint is. The constraint says the sides need to add up to 10, right? So we just want to maximize the volume. We want that to be as big as possible. Is that okay? Or is it not okay? In the constraints, first of all, we need the variables to be positive. Most people did that too. I think I saw that, and that's great. That's like something I'm looking for, right? You can't have negative lengths. But the other part is you want the sum of all the sides to be less than 10 or equal to 10 because you want to use all the sides. And when in class, I think with both classes, I said we want all the sides, the area of all the sides, to add up to 10. And some people wrote that down, which was okay. I mean, that's true. That was just like writing down what I said. But putting it mathematically would be this, right? There are two side lengths. The top and the bottom have area x squared because their sides are length x, right? And then the other four going around the outside have side lengths xy. And so there's four of them that have area xy. Right? So saying you want the area of the sides to add up to 10 is one thing, but putting it mathematically is the other thing. Because then if you wanted to solve this problem, you need to have the x's and the y's in the equation to move forward. Right? Because then the next step would be solve this equation for y or x, solve for one of the variables, and plug it into this equation up here. Right, so this is the test question. I would want you to actually do that. And the last time I did this quiz, I actually asked people to finish that. The reason I didn't want you to do it on this one is because I also had the second parts of the questions, but I think it's fair, in other words, to finish this problem. So anyway, it's important that we understand that because I'm going to ask you to do this on the test is what I'm trying to emphasize. So can I answer some questions on how to set that up or clarify why you thought something wasn't the case? Love to hear from someone because very few people got this one 100% correct. It'd be great to hear what the problems were.
All right, so the problem with this one that I had was just knowing which sides multiplied to which that eventually equals 10. So now I see what you did, so I get it.
So let me thank you for saying that and bringing that up. I just wanted to actually sort of remind you of the general layout of these problems, which I think would be helpful. Like if we just looked at, I know we only did a couple in class, we did a couple in the homework too, right? So if you look at the 4 or 5 we did, they're all kind of set up the same way where the objective function has a bunch of variables. It's not equal to anything. It's something we want to make as big or as small as possible. So you don't want it equal to 10 or something like that, because then you're literally constraining what it could be. You just have something you want to make big or small, right? So there should only be variables in it, in other words, right? That's what I'm trying to say. There's only variables in the objective function because you're trying to make it big or small. But then in the constraints, that's where you're starting to have some equation equal to some number, because you want to be able to relate the variables to some number, and that's how you end up, you plug it into the other thing, right? And so that's the way you should always think about it, is like the objective function is a bunch of variables. You want it to make it big as small. You use the constraints to help get you there, and so you need numbers in the constraints, in other words. And that's the way it always worked on this one too, for example, right? Objective function, just some number or some variables. You want it to be big, again, in this case. The constraint has numbers that are relating the variables. And if you look at the ones we did in the homework, it'll be similar as well.
Fair enough. When I was just looking in the notes, we didn't do like a cube one, so that just threw me off. But
well, it's similar to the one we did in the homework, though.
I know. I was saying in the notes though, so.
But your notes, you got your homework in the notes. I've been trying to emphasize that. I don't want to lose track of that, right? I don't know where this one is going to end up being, but if you write down the homework solutions, especially the ones we do in class together, then you can look at those. And I'm trying to make these quizzes look like the homework. I'm not going to be able to find it right now. But there was that one that was a box, right? It was like the post office makes boxes, blah, blah, blah. And we did, so it was a cube, in other words.
Mm-hmm. All right. Yeah.
Anyway. Other questions about the quiz? This particular question? I'm going to look at the other one in a second. I wanted to go over part B for question 1. Did you use all the sides when you were doing this one? Yeah, so the constraints, all the sides, the dimensions of all the sides add up to 10. Right, and so if we're looking at the square, it's hard to label them all, right? But there's 4 of them that are this side. There's this one, and then if you kind of walk around the outside of this, there's 4. And then there's 2 of them that are the top and the bottom of the box. Right, and so what I'm trying to say is the top and the bottom are x times x, which is x squared, and there's 2 of them. And so that's why there's a 2x squared in here. Right, and then the 4xy is there's 4 sides that have area x times y. Right, if you just zoom in on one of those sides, it's the base is x, the height is y. Is that what you're getting at there, Sebastian? And so that's where the 4xy comes from. You remember in the one in the homework, and I'm sorry I can't pull it up. I wish I should have renamed all these. I'm having a hard enough time just keeping track of them. But I guess if I looked at the dates, maybe I could figure it out that way. But whichever one we looked at, it was the one that had the UPS thing. We're close here. Optimization. It was the girth plus the length had to be less than something. Here it is. Right, so on this one, here we are doing the volume again. Right, we're maximizing that thing. It only has variables in it, and it's the same equation as the volume of a cube.
Yeah, same thing.
But our constraint in this case was this right here. The girth can't be less than 108. And we defined girth as being the perimeter, right? And so we just said, okay, if the girth can't be less than 408, then it has to be the perimeter plus the length, which is what it says right there, has to be 108. That's what led to, that's like this equation right here. It just depends on what you're looking at, right? In this one, it was the girth, which I know is some random thing that's defined here. But in the other one, it was just the area of the sides. Anyway, I don't want to, we can look at the other part there, but why is someone asked in the chat, why is the 2 sides, bottom and up, square, but not the other 4 sides? Can someone answer that question? Does everyone see that thing in the chat?
The length times width, they're both x. X times x is x squared.
Yeah, but how do we know that they're length x? Like, that's the question. How do we know the 2 bottom sides are x and the other one's y? What in the problem tells us that?
It says it's a square base.
Yeah, right here, right? It's a square base. So that's what led to having 2 side lengths x. And also, in fairness to myself, I went over this entire diagram when I let everyone pass out the quiz. I talked about the diagram. We labeled it together. I talked about why the 2 side lengths were x. And maybe you just don't remember. That's fine. But like, this is all stuff that I tried to sort of clarify when we sat down together. Anyway, these are good questions. Other things like that. All right, let's look at the implicit parts as well. And so you might want to, I know I wrote over top of it, so it's kind of hard to read, but you can look at the solutions on Gradescope as well. So I think the thing I'd like to sort of focus on, maybe just the first term. I feel like if we can understand the first term in both of them, we would feel pretty good about this. So there's things I'm trying to highlight right now. Just this first part. All right, so x times y. x times y in both cases is going to be a product rule, right? Because x is an x. In the first case, x is an x, and y has an x in it. And so they're both functions of x. And so that's why it's a product rule in the first case, right? In the second case, we're assuming they're both functions of t, and we're doing d over dt. And so there's like t's hidden inside of both of them. And so it's still a product rule. And so it's important to sort of realize first that they're both product rules. And then I think if we can understand how they're different, like here are the two solutions, right? How are those two solutions different depending on whether or not we're talking about t or x, then that might be helpful. So first, does it make sense that they're both product rules because they're either both functions of x or both functions of t? Is that okay? Make sure I'm taking a look at the chat here. Okay. And so then in the first case, we're doing d over dx, and then in the second case, d over dt, right? And so when we do the product rule on those, notice what happens in the d over dx case, right? X becomes 1 because we're doing d over dx of x. But in the other one, when you have d over dt of x, it becomes dx dt, because all of a sudden you're differentiating a different variable that's hidden inside of it somewhere. And we don't know what it is. We don't know what the expression for x of t is. We just know somewhere inside there, there's a t. And so the best we can do is just say, hey, well, whatever the derivative of this thing is the derivative. That's literally what you say when you say dx dt. You're saying, when I do d over dt of x, I don't know what it is. I just get dx dt, whatever it ends up being. It's kind of like a cop-out almost. It's like it's hidden in there. We don't really know what it is. We're just going to label it as dx dt, right? But the other one, since you're doing dx and it is an x, that's why it becomes the number 1. Do we see the difference there? That's like a critical thing that I want to make sure is clear between the two of those things. Notice in the y case, the y ends up being dy dt or dy dx in both cases, because in both of those cases, the variable's hidden inside of y, right? Y is either a hidden function of x or it's a hidden function of t. And so when we differentiate it, we don't know the answer. And so it's like the cop-out. We're just like, well, it's whatever the derivative is, dy dx or dy dt, right? And then the middle pieces are the same because you're not doing the derivative in the middle part. People see the difference there between those two things? I feel like if that makes sense, then the rest should make sense too. Just gonna pause there and let anyone say anything they want. Type it in the chat. Whatever, you could send me a direct message. A couple people did that today. If you don't want to, like, I don't know, out yourself as asking a question, it's fine to ask questions. You should feel comfortable with that. But so then, I mean, if that's okay, and again, feel free to still ask questions about the first part. Just notice how the other ones work, right? So the x squared one, that's a good one to look at. Notice the difference between those two. If you're doing d over dx of x squared, it just becomes 2x. Like, that's super easy. It's just a power rule. But when you do d over dt of the x squared, all of a sudden that's a chain rule, right? And this becomes the chain rule part of it. So notice the difference between those two. That's a critical difference between those two things, right? One is just a power rule. They both end up with 2x. Notice that. But with the other one, it's a chain rule as well. So then you have to do the inside part. Right? This is the chain rule right here. This is the chain rule part of it that I'm kind of highlighting in red. All right, I don't want to beat this to death if people are kind of getting it. No one's giving me any feedback here. I'd be happy to clarify it more, but right, actually everything on the bottom ends up being some form of chain rule because they're all, the t is hidden inside of there. Right? Notice how all those bottom ones are chain rules. I mean, the first one's a product rule, but there's a chain rule inside of it. I guess it's not really a chain rule. It's just kind of a normal product rule. Anyway, all the other ones are chain rules. Other questions about it? I'll go into more detail, but we're getting kind of late in the class here, and I'm not really getting much from you. So anything there? Okay, could you go into how you would solve for this? If it's not too much time, then it's smooth. It's definitely smooth. I'm not going to go into the full detail, but maybe I'll just give you the quick kind of steps here. The steps are always the same. And I know when you do algebra, sometimes it feels like every time they're different, but it's really not. So if you wanted to solve for, dy, you wouldn't really do it in the second one. You'd probably solve for dy dx in the first one. You do just one, get the derivatives on the same side. 2, you factor it out. 3, divide to isolate. I know that's a very just generic 3 steps, but every time you look at the back of the, the 4 or 5 we did, they're always the same. And I get that the algebra is confusing if you haven't seen it a bunch, but if you can keep those 3 things in mind and just go back and look at your notes at the things we did, we always got them on the same side, factored it out, divided everything away to isolate, literally every time. And I know they look different, but I would just ask, I can do them over and over, but it really takes at some point, you have to go back and just go through them yourself and then come back with questions, right? That's sort of what, I know I don't mean to put it on you, but you do need to do the learning at some point. All right, I'm going to jump into the notes. I want to make sure I get through a few things at least so that you can do the homework this week. I can't remember. Is this in the homework this week? I think this is in the homework next week, actually. So we should be good. Or it'll be smooth. I like that. All right. Other things before we get started? Other sort of general questions you want to talk about? We may end up class a little bit early too. So if you wanted to see the algebra thing at the end, I'd be happy to do that. All right, we're moving into the last section of the class. It's really exciting, actually. So, we've been doing all this stuff, just kind of moving back. This was L'Hopital's rule from last class. Everything we've been doing in the last, 3 or 4 weeks, derivatives. All right, derivatives, built them up, first and second derivative test, optimization, related rates, all that stuff's been derivatives. We're moving out of it, and we're moving into something else. This is the last section, and it's unfortunately going to use the word derivative. It's going to be involving antiderivatives, but at least the idea is we're not progressing further into this thing, right? We've kind of hit the apex, I would say, and we're coming down the slope on the other side. A little bit of encouragement. And the idea is we're going to think about first estimating the area under the curve. That'll lead us into the next concept of antiderivatives. And so here's sort of the main question I want to focus on today that we're going to estimate first is, how do we add up total amounts of some function, right? Derivatives tell us rates of change, and we can do great things with them. I hope you'll agree that we've solved some interesting problems by thinking about rates of change. So instead of rates of change, how do we add up total amounts of a function? For example, didn't do that. For example, let's say we've got this function and it tells us the number of births that are taking place at a certain point in time. So it's like a birth rate kind of function. And we want to know how many births have taken place past some interval or between 2 numbers or something, right? So from A to B, for example. We would basically want to add up these individual function values over this interval, right? And so let's draw a picture real quick and then we'll understand what we're talking about here. So I'm going to try to draw the same picture twice. One's going to be the exact value and the other is going to be the estimate. And so let's both try to draw the same thing twice. Try to draw kind of like an extreme x squared value, or maybe almost like exponential looking. So something that's kind of like this. And try to draw the same thing twice. And so this is our birth function, right? This is our f of x. Tells us how many births are taking place, and x is on the x-axis, of course. And so the births are going up, right? We're having like more births. Most populations, especially human populations, are going up. The birth rates are going down lately. And I think I read, I think it's Japan who actually had a negative birth rate for the first time recently, which is pretty unheard of for humans. Anyway, so let's so that's our birth function. I didn't quite do it the exact same way. Oh, I should have taken advantage of my ability to copy and paste this thing. I think I'm going to try that. No, I'm not going to try that. It's going to take too long. Okay, so we got the same function, and we want to do the birth between 2 points. So I'm going to label that A to B. So make A kind of pretty far to the left, make B over on the steep part of this thing. Maybe right at the end of it. So, every single point on that line, which I'll just kind of do a couple dots here and then I'll erase them. But every point I've just dotted on that left line tells you the number of births that are coming out of the time. So if we want the total number, we would want to add up all those points. But points, there's infinitely many points between A and B. Right? Think about that for a second. I know it kind of looks like, oh, you just drew a couple of them. And if you filled it in, you get them all, right? But between any two numbers, there's infinitely many individual points. So we can't just like add them all up. But what we want is that area. We want each function value, which in essence is telling us this area. This is going to be what we want to determine. Try to fill that in best you can. I guess I can cheat a little bit and do this. And this is the exact value, of course, right? If I could somehow do this area, we'd be in business. But it's like not a normal shape. If it was like a square or a rectangle, we'd have formulas for that. But we don't know the formula for this shape, right? And so this is the exact value. So I gotta make my thing again. But we need advanced techniques really to do that. And so we're going to learn about this in the next section. But that's really what we're after. And that's what I always like to start with, is like, this is eventually what we want to do. And actually by the end of class today, I hope to kind of introduce the idea, but we want that exact area. We're not quite ready for it. And so what we do in this section is what I'm going to show you on the right, which is to approximate the area. And so the very classic thing we always think about and usually leads into the next step, because we take a limit, so we kind of connect it to past concepts. Anyway, is thinking about, okay, well, I don't know the standard, I don't know the formula for this shape. So let's just come up with a formula of a shape we know, like a square, for example, or a rectangle, and estimate it with a bunch of rectangles instead. And so in this section, what we do is we estimate it using area of rectangles. In case people are still drawing that. And so instead of getting the exact area, which we'll kind of get to next time, we're going to think about, okay, well, what if we just estimate this by putting a bunch of rectangles underneath there? And so let's see what that looks like. Let me get another color out here. I'm going to take my interval, A to B. Let's break it up into a bunch of equal size pieces, and then we'll put a bunch of rectangles underneath there. All right, so that's, maybe I'll just make that note here. I'm going to break up into n, and in this case, well, let's see, I'm not sure how many we'll do. N equals something equal size pieces. How many can I get in there? Maybe 3 or 4. Let's find out. Maybe like 1, 2, 3. So I drew 3 lines, but there's 4 actual pieces, right? Oops. So there's 4 pieces right there. And I'm going to label them. A is going to be the starting point. The first one's going to be x1, x2, x3, and then the last one is x4, right, the ending point. So you can see there's going to be 4 pieces there. And that's going to be the base of our rectangle. And I'm trying my best to make them equal size, right? And then notice how if we stick some rectangles under there, we can make either side touch the top. I'm going to make the left-hand side touch the top. And so here's my first rectangle. Here's my second rectangle, third rectangle, 4th rectangle. And so I'm trying to use the notation from down below. If you scroll down and you look at your own paper there, n equals 4 is going to tell us how many rectangles do we have, right? And so you can see I've got 4 rectangles right there, but notice how there are 5 x values, because if you want to have 4 rectangles, you need to have 5 pieces, right? Excuse me. And the other thing I'm kind of pointing out here is we want the exact value, which is on the left. This is an okay approximation, but it's certainly a bunch of error in here, right? If I kind of zoom in on this and I think about, well, I really wanted to get right up to the graph and all this gap, and the gap gets worse as the graph goes on, right? Look at this last gap. This is a huge gap that we're missing right here. This is what we would call error. We wanted that in part of our calculation and we missed it. And so something we're also going to talk about is how do we minimize error? That's a huge topic in sort of advanced math and just general, I mean, anything really, especially computing if people are in computer science, minimizing error, right? Making things optimal. How do we get that error down, right? So we'll talk about that as well. People have any thoughts about how we can get that error down? We'll write it down later, but ideas? Maybe just plant the seed if no one wants to contribute that idea now. Maybe think about how would we make that red part smaller? Right? What are some things we could do that wouldn't do that? Anyway, we'll keep going here. I'll get we'll kind of formalize this mathematically, and then we'll do an example. And then I hope to, based on the time, I think we might be able to start the next idea and kind of, I don't like to spend too much time in this. It's like this fake estimate thing that eventually we're just going to say, yeah, forget that and let's get the exact value. I like to set up the idea, but not waste a ton of time on it. Yeah, so a couple ideas to minimize that error. If we want to make that error smaller, and we'll write this down at the bottom, but yeah, either adding more x values, so maybe more rectangles is what I'm hearing, right? If you have more rectangles, you can get kind of closer up into the graph there. Smaller rectangles and squares, yeah, so same idea. Maybe another idea that you can think about, I'm not going to show you it, but another idea is a different shape, right? So rectangles are a shape that we're using because we know the area, but maybe there's a better shape we could use that we also know the area of. For example, trapezoids is the other one. A trapezoidal rule is a different one. Anyway, we can make a couple of those notes down at the bottom here. All right, questions about anything I'm trying to say there before we formalize this? It's good to get, and this is kind of the difference if we're talking about the quiz we just looked at, the difference between getting the idea of something and then actually writing down the math part of it that carefully lays it out, right? So for example, saying, I want all the side lengths to add up to 10, or the area of the sides adding up to 10 is one thing, but writing down what that means in terms of the actual math isn't more important. Okay. And so the key idea here is the thing we've just been working on. We've just added up a bunch of function pieces. And so here's how we do it mathematically, right? This is formalizing mathematically. It's always going to be these 3 steps. The first step is always to just break up the interval a to b into different pieces. And we define what the x values are, just like we did in the second ago. And then we're going to add up each function value and multiply it by delta x. And let's talk about that in a second. Let's do these step by step here. So the first one, right, this first thing is sort of telling us b minus a over n is going to be the end point minus the start point, right? So you're figuring out the width, and then you divide it by the total pieces. And that'll tell you how many x values you have. Or I'm sorry, that'll tell you the step size you want to take between them. Right? You want to think about this as like a step size. And then we step along. So notice how this is a delta x thing, right? I didn't mean to undo that. I wanted to erase that. Right, so we're calculating delta x here, and then delta x gets used in all these locations. right? So you sort of take a step of delta x from the beginning to the end piece is what this is saying. I think sometimes it helps maybe to draw a slightly different picture here. So it's like, let's do a linear picture. You start with A, that's your x0. You're going to end with B, that's your xn, right? So your first point and your last point. And the way you get between them is by taking size steps of delta x, right? And so you'll have like x1, x2, x3, dot, 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 xn minus 1, all the way to the last one. And what I'm trying to point out here is when you walk from one step to the other, it's size delta x. Oops, not the last one. There we go. I know this looks complicated with, if I didn't have the picture there and you just looked at this thing that says x1 equals a, x2 equals a plus 2 delta x, that looks confusing. And so if you just have this picture, you're just saying, oh, we're just kind of like walking along size step delta x.
How do we know how many ends we should, or how many pieces we should divide it into?
Yeah, so in terms of like practically speaking, the problem will just say, hey, use this many pieces. Like, for example, we look at this this example here. It says let n equal 10. So it's one of the things that's given. And if you were going to choose it, you would just choose around. You'll never have to choose it yourself, though. It's always part of the problem. Yeah. Okay, and so then we want to add up the area of a bunch of rectangles, right? And so that's what the next part says. Step 3 says, then we want to add each function value at each point and multiply it by delta x. That's because the formula of the area of a triangle or a rectangle is base times height, right? And so leave a bunch of space here, but just kind of on the side here, let's just draw a generic rectangle. Maybe this is at the point x1, x2 or something, right? The base is, if we wanted to know the width of the base, it's going to be delta x. Whatever delta x is the length of the base. And then the height is the function value. And so the area of this thing is the function value times delta x. And so that's why when you see this thing down here, or here for that matter, you're adding up a bunch of function values times delta x, right? Base times height. So you're adding up the area of a bunch of rectangles. Now I'm going to draw a couple more pictures in the middle here, so it'd be good to leave some room, or maybe you can have another page or something if you want. But I'm just trying to explain these formulas so far. These are adding up base times height of a bunch of rectangles. Now, I'm just going to try to draw that same picture again, I guess. Notice how there's two options here, right? There's this number 1 and number 2. And what I want to do is draw 2 pictures that sort of show what each one of these things are doing. I always debate, like, should I just put these pictures right on here? And I usually think like there's some value in having you actually put pen to paper on these things to write it out, kind of experience it a little bit and seeing like, oh, these are the different x values. We're taking steps of delta x, etc. Anyway, so I'm going to try to rewrite that same thing we just did a second ago. Let's get it set up. Let's not quite finish it. So we'll go from A to B again. And we'll do, and I did not do a good job of doing the same number of steps. Let me make that a little bigger. We had 3 intermediate steps, right? 1, 2, 3. Okay. So we started at x0. This is x1, x2, x3. x4. All right, let me stop right there. What's that x before the b? Can you clarify? So someone in the chat said, what's that x before the b? I'm not sure what you mean. x3? Is that what you mean?
I think he meant x minus 1 in the example before. I mean, n minus 1.
Oh, this thing right here.
Yeah.
This is, so I was counting up. So this is, notice how I've got like this ... thing here? Okay, yeah. So this is like common math notation. It's like, we don't know what n is, so I don't know how many x's there are here. And so I'm trying to do an example of like, oh, well, the first one's, or the 0 one here, the first one there, the second one here, the third one here. And then there's some amount in between, right? And then this is the last one. And so what you write to represent the one before the last one is x sub n minus 1. So that's what that says. It says the x value 1 before the last one is the way you think about that, n minus 1. Sorry that I know it got a little, there's a dot underneath it, which is confusing there. Other questions? Okay, so what I'm trying to set up here is everyone's set up to watch this, because it'd be good if you looked at this, right? So there's two different formulas, right? One I have labeled number 1, one I have labeled number 2. The difference is when you write rectangles, you need to decide whether or not the left top of the rectangle touches the graph or the right top. Like in the example I did up here, notice how it was all left top. So I'm going to highlight that a little more in blue, right? The blue dots I'm kind of writing in there. The top left of the rectangle touched it, and therefore we had an underestimate. And so let's just kind of remind ourselves about that situation. That looked like this. When you have the left top touching, it looks like this. Right, we have 4 rectangles, the left top is touching. It's an underestimate in this case. Right, we have all this error between the graph and the things that we wanted to capture. We really wanted that error, and so this ends up being an underestimate of the actual area because we have that missing pieces there. All right, so this is the same thing we just did, just kind of reminding ourselves. What I'm trying to point out here is if we let the right top touch the rectangle, it'd be a perfectly fine way of doing it, but then we'd have an overestimate. Right, so let's do the same thing, but instead of having the left side do it, let's make the right side touch the graph. So we still have error, right? So now the error is above the graph inside the rectangle. And so we added up these rectangles, our estimate would be too much, right? This would be an overestimate, or the other one is an underestimate. And the point I'm trying to make is it depends on whether or not you use the left or right endpoints paired with the shape of the graph. That's important to note too, right? It happened to be over and underestimate in this case because the graph was going up. If it was going down, it would be the opposite case. But just knowing that one is going to be over and under is what I'm trying to point out here. I let people finish writing this down here. Let's see if there are questions about what I'm trying to say. And I see someone says, wouldn't you be able to solve for that gap if we're using the top left be the height when it's touching the graph? Wouldn't you be able to solve for the gap if you are using that top? Can you clarify what you mean by that, Sebastian? I'm not really sure what you mean. Yeah, go ahead.
I kind of thought about it as like, if you're gonna use the left point as the height, those all just look like a whole bunch of right triangles.
Oh,
So
I see. Like,
I
couldn't you
would
figure
assume
out
you
what
just
those
be
things
able
are?
to solve for that like gap in there, and then you wouldn't have the error no more.
Yeah, that's an interesting point. So your point is you've got like you'll end up with a bunch of things that look like right triangles, like these things. And so can you just like figure out what those areas are and then figure it out? Yeah, that's a good idea. And actually, so first note that they just kind of look like right triangles. It's really a curvy graph. And so it's going to be, that's not straight. And so it's still going to be an estimate, even if you were able to do that. And you're actually getting at the idea of what the trapezoid rule does. So the trapezoid rule, instead of putting rectangles under there, it puts trapezoids, which do this. And so the top kind of goes at an angle and cuts off the error a little bit. So it kind of incorporates, in some sense, the triangle into the top of the graph. So that's what's called, I'm going to erase this in a second, but if you're interested, I'll write it actually on a different page. It's called the trapezoidal rule, I think. I think there's an AL on the end of that. And it's like a better estimate. But all these things are just estimates. I don't want to, sometimes people kind of go into that and do different estimates. I'd rather just get to the kind of the exact value and not spend too much. But yeah, that's a good thought. And the trapezoidal rule does just that. Yeah. Other things, that's a good thing. Other thoughts like that? It's also only a triangle in this case because of the way this particular graph is shaped, right? If the graph was shaped some different way, there may not be a triangle in the gap there. Okay. Other things? So notice n is 4 in this case. I just want to kind of clarify that. We could have more rectangles. We just have 4 in this case. And what I'm trying to point out as a reminder as well, red in this case is the error. Right? You're either getting too much or too little, depending on whether or not you use left or right endpoints. And so here's how we actually formalize that, right? Down at the bottom, you guys seen this notation before? We haven't seen that in this course, I don't think. Do you know what that means?
The sum of?
Yeah, so this means the sum of. Kind of write it off to the side there. And so we're doing the sum of, and then the I equals 0 to n minus 1 part. That means you're taking I and you're moving it between 0 and n minus 1. And notice where I is, right? I is here, and then it's also here. Right, so if we kind of write out these terms, this is going to be F, and you can, delta x is multiplying it every single time. Let me actually start there. It's multiplying it every time. The thing that changes is the F part. And so you can actually just factor out the delta x, and then you don't have to write it the whole time. Hopefully that makes sense. And then, right, so I goes from 0 all the way to n minus 1. So I'm going to do that same notation, dot, 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 all the way to the second to last one.
So did you do any estimating the area under the curve, any stuff like this in your pre-calc class?
No.
No? All right, because I know I didn't have you, but I must have done this in high school because it looks very familiar.
Cool. That's great. Yeah, I didn't do that in mine. It's possible people do that. I actually just started looking at a different pre-calc course of this online thing that I was looking at. And the stuff they do in pre-calc is very dependent on the school, is what I've kind of seen. Pre-calc isn't super defined. Usually it has some trig in it and some form of algebra. But anyway, people see what I'm doing there. So on that particular one, notice how you start with the first one and you only go to the second to last one. And that's what happens here. You go to the first one and you end at the second to last one. Where the next one is going to do the opposite. It's going to start at the first and go all the way to the last. Right, so if we write out the second formula, get a different color here. This one's going to be delta x. Notice how n starts at 1 and it goes all the way to the last. So we're going to have f of x1 all the way to the last one. All right, we're going to do an example here. Just a moment. Any questions before I slide down and look at that example? We'll relate it back to this steps in a second here anyway. So, all right, so we're gonna actually do this exact example. So the curve I've been drawing is just generic, but it could be the curve x squared plus 1, right? And so if you think about x squared plus 1, it does this. And so it kind of looks like the right-hand half of that. And we're gonna go from 0 to 5. And so we're gonna kind of look at the same kind of piece of a graph we're looking at, right? And so that's our A and our B. And so we're just gonna break up the interval, plug in the points, get the estimate. And notice how it's telling us to do both upper and lower sums. That means use right and left endpoints. And I actually didn't label that in my last thing, did I? I think I need to label that. Don't really have room to label it. So I'm just going to throw this label right here, unfortunately. So the first thing I did is left endpoints. That's this thing right here. And then right endpoints is the other one. I can slip that underneath. Right, remember again, it's like, does the top right touch it or does the top left touch it? The first thing we did was the top left. The second thing we're looking at is the top right. And we're just going to kind of do both of them. And we're going to write all the function values down and basically you just choose to use all of them. I mean, do you use the right-hand half or the left-hand half? Anyway, you'll see it in a second here. All right, let's set up the problem. So we're going to do steps 1, 2, 3. 1, 2, 3, right? So first thing, break up the interval. We're going to use 10 pieces in this case, and so it's going to be a little bit longer, but we're going to get a good estimate. And so number 1, figure out the step size. It's just b minus a over n. In this case, b and a are 5 and 0. So 5 minus 0, right, in the top there. And then we're being told to use 10 pieces. So n is 10. And so all that tells us is, we get 5 over 10, of course, or 1/2. That just tells us the step size we want to take between the x values is 1/2. And so, we're walking from, the other way to say that is, if you wanted to take 10 steps between 0 and 5, they have to be size 1/2. And so you don't even need a formula to kind of think about that. How many step sizes do I need to take to get 0 to 5 in 10 steps? Well, 1/2. And so that becomes the second piece. What are the x values? Do you need to write this down? Do I need to see this? No, but I'm trying to be clear about how this works. How do you formalize these things mathematically, right? So x0 is the first starting point, which is this case is 0. And then we're just going to take half step sizes all the way up to 5. Right? So x1 is going to be 0 plus 1/2, which is 1/2. I'm going to try to write a little bit better. x2, just take another step size. Just keep on stepping along all the way to the very last point, which is 5. So hopefully you're with me that each one of these delta x, you're doing delta x equals 0.5. delta x equals 0.5.
What is x2 equal to?
You tell me. If we started at 1/2, right? X1 is 1/2, and then we take a step size of 1/2. What do we get to? We're just taking steps of size 1/2. So 0, 0.5, 1. Oops, I just said it. 1. Right. So this says 1/2 plus 1/2. Maybe that's what your question was.
Yeah, thank you.
We're just kind of breaking up the interval. Other questions? Okay. So oftentimes when I'm in person, I will show people how to kind of calculate function values quickly on a graphing calculator. If you have some trick you like to use to do that, that'd be fine. I usually don't put involved questions on tests or things like that, but I'm just going to make a quick table. I did this ahead of time. And if it's not clear what we've done so far, the x values are as follows, right? We started at 0, and we're just taking steps of 0.5. So it would be like 0.5 is the first one, then 1, 1.5, 2, 2.5, 3, right? We're just step sizing 0.5 all the way up to the ending point. And we need the function values, right? We're going to plug, you want the heights of all the rectangles. And so I just did this ahead of time in my calculator, and I got all the outputs from these locations. You just plug it into the formula. And I got as follows. And we're going to use all of these for different parts of this. And so I thought it'd be good to just have them all written down somewhere. So this right-hand column that we're writing down right now, I obtained by plugging the x values into the function. And I'm going to be real tedious about this one example because I want it to be totally complete when you're looking at it later. Because the third step is to do the 3 formulas or the 2 formulas. So that'll be step 3. Let me just pause there and see if people have questions or need to catch up. Chat looks clear. All right, so let's do the 2 formulas, right? So there's 2 formulas at the bottom of this page that we kind of wrote down. And we'll do 1 and 2. And so it's either left endpoints or right endpoints, right? So the first one, if we wanted to use left endpoints, which is going to end up being an underestimate in this case, the area between the function and the x-axis is approximately that formula, right? So that formula was delta x times f of 0, 0.5, all the way up to the second to last one. This is the first one. This is the second to last one. And so if we're thinking about the chart that we just drew, we drew, we're doing the ones I'm highlighting. we're not including the last one. We're going from the first one to the n minus 1. So 0 to 4.5. We're leaving out the last one. Again, look at the picture. Right? You don't end up using this last function value on this one. You only end up using it over here. Questions about what I'm trying to say there? I'm going to write this out still and kind of be as clear as I can about it. All right, so let's plug those numbers in. So delta x was 0.5. So 1/2. And then we add up all the function values except the last one. So 1, I think I might have enough room to stick them all in here. Let's see. If you get this, feel free to not write them all down, but it's a good idea to write them all down because if you get confused later, you can have these in your notes. You can look and say, what numbers did they use to get that? Oh yeah, I wrote it down. Right, so I'm starting at the first one, going to the second to last. Easy calculation, right? We're adding up a bunch of rectangles, but we don't quite use the last one. And so this ends up being 1/2 times 81.25. So this is an underestimate of the area. And we're just going to do the same thing, but we're going to do the right endpoints, right? And so the right endpoints is going to be the x1 all the way to the last one. Questions about the notation on this sometimes is the tricky part. Anything about that at all? Okay. So let's use right endpoints.
And then so we take the average of both once we're done.
If we wanted like a really great estimate, yeah, we could average both of them. Yeah, that is something I would point out. Exactly. Depends on the question, right? A lot of times these questions in the homework and what I oftentimes just do on tests is to say, just estimate it using right endpoints or left endpoints. You know, if we want the exact value or a really good value, we're just going to do the exact thing that we'll look at next time. Other thoughts before we keep going? So I'm just going to write this one out again. So the area is approximately delta x. And then instead of starting at 0, we're going to start at 0.5, right? Start at the right one. And we're going to go all the way to the last one. So f of 1 all the way to 5. Right, if we kind of highlight the area we're using these pieces. We're not using the first one. We're not using the 0, 1 piece. We're going the second half. We just plug the numbers in, right? And so it's going to be a bigger number. It's going to be an overestimate. So 1.25, 2, 3.25, 5. I'm going to tediously write them all out just because I love it. Just love getting this estimate. Oops, gotta write the correct numbers though. And so in this case, when you end up doing it, you get 53. Gosh, horrible. And so as John's pointing out, the real estimates, the real area means between the two of them. If you wanted a great estimate, you could average those two things. I'm not going to necessarily ask you to do that ever, but you know, it's at least noting that the area bounded between our function and the x-axis is between these two numbers. All right, great. Just looking at a few of the homework problems related to this while people finish writing things, and I think they're not too bad. Again, this is next week though, so no rush on that. There are a bunch though, so some kind of set it up for you, ask you to think about it. Some are asking you to do the whole thing, kind of like we're doing now. You know, when you use different functions, they have different shapes, and so different things happen. That's kind of what we're exploring in some of these problems. None of them look terrible though. Questions? So I just wanted to add those couple things that we said too that we're not going to get into the next section. We've got a few minutes left, and it'd be good to talk about how we can improve this. Always good to think about how can we improve the estimate? Because, you know, thinking about how people actually came up with the exact value sometimes, they probably started with these estimate ideas and then thinking about how to improve it. And eventually you get something, you work towards the exact answer. Someone said, what's the word after area in the bottom thing? It says bounded. Yeah, I got to work on, when I get to the bottom of these pages, my hand slides off. Handwriting gets extra bad. Okay, so someone had said we could use a better method. And if, you know, if we, oftentimes this happens in high school. I feel like I remember in high school going into the trapezoidal rule. Is it trapezoidal? Now I feel like trapezoid method, trapezoidal method. Is anyone familiar with that method that can confirm that? Trapezoidal method. I think if there's an AL in there. And I would just encourage you to take a look. You can just see Google if you wanted to look at that. But the idea is you have the curve, right? If we're trying to estimate the area under that curve still, trapezoids have an angled top. And so instead of just doing a rectangle like that, you instead connect those two pieces with like an angled piece. And so you just kind of get closer up to the graph, right? So there's less error. That would be a rectangle. That's a trapezoid. Just kind of get closer up to the graph. And the other thing that someone has said was more rectangles. And that's a really key thing, because in the next section, we're going to talk about when you, well, let me just draw the picture first. I just love drawing these pictures. If I don't mess it up, this usually illustrates the idea. If you want to do the same kind of thing, but we only have a couple rectangles, we have big gaps there, right? But if we kind of stick more rectangles in there, we end up getting closer to the actual graph. Right, so there's some error. This one's going to have less error. And so what we'll see in the next section, if you kind of page to the next page, is if we take the limit as n goes to infinity, right? So we throw a limit on the expression we just dealt with. That implies there's somehow infinitely many rectangles, right? If we could stick infinitely many rectangles under there, whatever that means, we would get right up on that graph and we would get the exact number. And so I believe that's what it says right here, right? This is going to be, we'll see this next time. This is the exact area. And you can see it equals, if you take infinitely many triangles, or rectangles, excuse me, I keep saying that. Yeah, somehow had infinitely many rectangles, we would get that exact area. And so that's how we usually bridge this concept with the exact area. All right, I'm going to stop there for right now, but I'm happy to talk more about this, or if people have questions about homework or anything else, the quiz, I'll stick around. If anyone wants to see that algebra thing that was being asked about, let me know. Otherwise, I'll just see you guys on Wednesday, right?
Have a great day.
Thank you.
I'm just gonna finish writing this last graph, and then can we go over the algebra stuff
Yeah.
for the quiz?
Sure.
For sure.
Is
Thank
everyone
you.
else still writing? Well, you let me know when you're done writing this one.
All right, bet. Okay.
Someone else all set writing stuff?
Yeah.
So let's. Oh, it was on here. So let's do that thing. I'm going to insert another page here. Let me rewrite it down here. So I'm going to rewrite the problem, but instead of writing dy dx, I'm just going to write y prime just to make it a
That's
little
what I did on the test. I was gonna ask you about that. Do you want it in the dy over dt or dy over dx form, or you feel like y prime is fine?
Y prime's fine. Yeah.
Okay.
Sometimes if I write y prime, people get confused because they're not sure if it's a prime or not. So I try to be clear when I write solutions to be. It's hard to mess up. Oh, dy dx is obviously the derivative. Anyway, yeah. So this problem was 1 times y plus x y prime 2x. Yeah, were you one of the people who tried to solve it?
I'm pretty sure I did, but yeah, I spent a lot of time just genuinely trying to solve the problem, and I'm pretty sure I got the answer, but I messed up on the 3y. I just put 3y. I didn't put the 2 when I took the derivative by accident. So that messed me up. But other than that, it was pretty smooth. I just wanted to learn how to solve so that I know for the future. You said put all the y primes on one side.
Yeah. So
And
these
then-
three are going to go over there, right? So it'll be like. And then the other stuff moves over. Is that all right?
Yeah. And then you factor the y prime out.
Yep.
And then it's just simple solving.
And that's pretty much it. I mean, it's ugly as hell, but.
It really is. I don't know how you about to take cosine y. I don't really know. It's looking real slow, honestly.
It's a total made up problem that would probably never really happen, but I just threw a cosine and an e in there just to have those in the problem.
Man, I don't want to have to do the what's the derivative rule for fractions? Like it
Quotient.
starts with a Q.
Quotient
Yeah, I
rule.
wouldn't want to do that for this one. This one looks like pain.
It's not too bad. There's actually, right, cosine becomes sine, e to the x stays the same. This one's not horrible. There's no chain rules or anything in there, at least.
With this cosine already being a negative, you know how cosine changes into a negative sign? Would it be positive sign then?
Yeah, exactly.
Okay.
So it'd be like minus sine.
Yeah. Okay. All right, that's smooth. The part that really messed me up and that I got the lowest amount of points on was the first question. That's what that little like I think you said 2x squared plus 4xy. I didn't get that one.
Did you see what we were saying about that?
Yeah,
So
no, I seen it.
Okay.
I seen what you were
And
showing.
I know it's
me,
confusing.
how-
Like I know that's why I tried to clarify it a little bit in person, and I know it can be hard in the moment of a quiz or whatever, but yeah, adding up the area of all sides, we would kind of want to think about what's the area of one side, how many sides are there? That's kind of the process, right?
Yeah, now that makes more sense. but for sure, I won't be getting that wrong on the next one.
Okay.
For the test that's coming up, it's the final test, right? This is gonna be everything.
So we have one more regular test and then we have a final exam.
Oh, the final is gonna be cumulative.
Correct.
Okay, just making sure. Are we gonna have like study sessions in class after we're done with all the material? Because we're on like page what, like 54, and there's like 75 pages in here.
Yeah, I think the schedule has one or less classes maybe for review. And then I'll probably schedule some like additional optional sessions.
Okay, for sure.
And you still need to figure out the final day. I was just thinking about that. I have to double check, but they made some rule about finals that's different for this semester. So anyway, I have to double check that.
Are we gonna have to be physically on campus to take the final? Like we go and take tests?
Yes.
Okay. All right. Well, I appreciate you staying after and explaining with me. I hope you have a good rest of your day, man.
You too. Take care.
You too. Be easy.
How are you doing, Janetta? Can I help you with something?